variety si tady to máš taky známý z člověk, který tebe analyzuje z motoru a hledá tam prostě, co si špatně, no přes ty meetupy.
Hello, I'd like to make a short, around 30 minutes presentation, and then we can have some Q&A. So this session will be a little bit shorter, perhaps, but we will get more information maybe with more facts together, and we'll be free to continue working faster. So the presentation is about a small tool which uses neural network to place punctuation into unpunctuated text. Its main application in practice, or its main use case, is a small Android app which developed over here. So it's an Android application which you can save mobile data, right, while watching YouTube videos by just downloading captions, getting them punctuated by the network, and reading only the captions, only the subtitles. So if you are only interested in what is being said, and you are okay with the automatic transcription quality and the punctuation quality, it's sort of okay. I personally use it. If you wanted to use it, I think you would be unhappy about the fact that the APK is not available on Google Play and not even on F-Droid, this open source store. So you would have to download the APK or compile from source. So maybe just a quick demonstration to understand, the use case first. So you take YouTube URL, you paste it, then the captions are downloaded, and you get displayed text with some dots, with some generated dots inside the text. The dots not always correct, are not always placed correctly, but it's much better than not having any punctuation at all, no dots. Because without it, you would just get really huge wall of random, well, not random, but undivided text. It would be much harder to read. So how core of this application actually works? Let's look a little bit in the detail. So as I mentioned, there's this neural network there, which is made up of three layers. If you are familiar with them, I will go into the detail to them later. So first there's this embedding layer, then there is a convolutional layer, and the output is a softmax mesh layer. It's written in this simple Python API library called Keras, which is used for simple, quick neural network programs. With it you can train and execute, you can iterate very quickly. So in specific how this punctuation works, so I train the network on the data where I'm training the network to place a dot in place of any of these characters. So the network tries to say, is there any of these characters, and if it is there, if it predicts that there is any of these, it places a dot. It says yes, it's there. Between these words, there should be a dot. So this project is also standalone, so you can use it as a command line tool to produce, convert from unpunctuated to punctuated. So you can and after, you can, for example, punctuate your subtitles if you download them using some other tool like YouTube DL on Linux. I was inspired to do this. I was inspired by another project which already performs very well. It is more advanced, and it is described. It is also published on GitHub, and it is described as a bidirectional recurrent neural network model with attention mechanism for restoring missing interword punctuation in unsegmented text. This inspirational project uses this much harder to read framework, which also wasn't suitable for Android, because with Keras and TensorFlow backend you can run your neural network apps much easier. So that's what I'm using. Also, it uses a little bit more complex or more harder to understand network called recurrent neural network, while I'm using this convolutional one-dimensional neural network. Also, this other project apparently takes longer to train, although I wasn't, that's just based on some comment of somebody comparing those two projects. But on the other hand, the project is more advanced. It also predicts exclamation marks and question marks and so on. So to explain this project, I would like to go through basic data flow, how sample data or training data flows through the different layers, and what is the actual output. So first step is data preparation. So to train the network, you need quite large segment of text. I actually trained it on around 5 million samples, 5 million 30-word samples. So that's quite a large amount of text. So firstly, I was using this European Parliament transcript data, but that was, in the end, it was a bit suboptimal because the language that is used, I think that is because the language that is used in European Parliament is a little bit different than the language that we on average use in some popular YouTube videos. So, for example, the sentence length seemed to be much longer in European Parliament data. They also use unusual words. So that's why I, in the end, went with different data set, which is based on some news commentary data. So after cleaning the data set from some unusual characters, we also need to map the words which we have into tokens. This is done by analyzing some body of data and looking for 20,000 most common, most occurring words, and only these words are then considered during training or during prediction. So the network, the model of the network only sees these words, and all other words it sees as unknown token. So it is basically as if you knew only 20,000 words, which still isn't actually that bad. So when you have this word index, when you build this word index of only 20,000 words, which each word have one number associated with it. You can then take your sample of training data and map it into these integer numbers, into numbers between 1 and 20,000. And when we do this, we have data prepared to ingest into the model, into the first layer. So then, how the model actually looks like. So from here, from what you can see now on the screen, you can see that the Keras API is very, very readable. Not only that it's written in Python, where you can avoid lots of things simply by just the language, but also you can see that you are here reusing lots of standard things directly with reasonable defaults from the Keras API. For example, here we have a one-dimensional convolutional net. So that is just a function that I simply use from the framework. And the model is, as you can see, constructed by just adding the layers in sequence on top of each other. So we ended the previous section with having these tokens, but to actually create samples from these tokens, we cut sequences of 30 consecutive tokens, and those 30 integers, these 30 integer arrays are then used as an input for the first layer of the embedding layer. So the embedding layer, the first layer. That's I will not go too much into details, but the embedding layer is as an input it takes these words, it maps them into quite high dimensional vector space, but which is around 100, 200 dimensional, 100 to 300 dimensions, and it is very useful because when you map different words through this embedding layer, you get vectors which in different projections are these vectors, if you look at them in certain projections, are located very closely to each other if they are within the context of the projection, sort of related. I'm not sure if you saw some examples already on internet. So, for example, if people did projection of good and bad, and then looked which words were analyzed as being close together. So the things that were perceived as being good in the training set were closer on the axis of good and bad, closer to each other, and more to the right, moved more to the right in the way of good. So we'll read here description from the graph embedding data that I used. I downloaded and raised weights from this graph network. So this graph is unsupervised learning algorithm for obtaining vector representation of words. Training is performed on aggregated global word-to-word occurrence statistics for a corpus, and resulting representations showcase interesting linear substructures of the word vector space. That's layer we can see here is the convolutional one-dimensional layer. Can shortly describe what it means. It basically means that we have 512 different small networks which have input free tokens, or which have free inputs, free these outputs of this embedding layer, and these 500 networks are then just then applied one by well, basically slide it across the sample from, you can sort of like from left to right. It follows all. We get outputs from all the positions in the text, and then all the outputs from all the positions and all the different types are then used as an output. Let me read shortly also the Wikipedia description. It's shift invariant or space invariant artificial neural network based on its shared weights. So here the space invariance means that you take these small networks and you apply them on first free, then the one step to the right free, and one step to the right free. And this sharing weights means that you have just 500 of these, and you just apply them on different positions. So based on its shared weights architecture and translational invariant characteristics. So the next layer during training is it's not actually a layer. It's actually implemented as a layer. It's an training layer called dropout, which is used for regularization to improve the training a little bit. It that actually turns this layer turns off randomly in each badge. It turns off some of the outputs, and that improves the training. And the last layer of the model is called dense layer, and it has only 2 outputs. And also it has an additional function applied to those outputs, such that if those are 2 float values, and if you sum those 2 float values, you get 1. So this we then interpret as a probability, whether the network thinks rather that there was punctuation in the text, or whether there wasn't. So if we get, for example, 0.9, that there was some of the punctuation marks, characters, then we would evaluate it as during training, okay, there was, or during the actual filling in the dots, we would say, would place their actual character of dot. So I have here some visualization of the network from the TensorFlow dashboard tool. If you look a little bit zoomed this way, you can see here that this display displayed in such a way that we have two outputs here. Then we have convolutional layer also split or displayed into two parts, and the embedding layer also here in two parts. So how does this?
Sorry, just a second. Could you please elaborate a bit more about this graph? How does it also vary the data which we use for the training?
Okay. So here we are inputs. So here we have those. Here we have 30 integers on input. These are, and those 30 integers are then mapped to 30 vectors. And those 30 vectors then go to the convolutional layer, and we get 30 times lots of 200 512 outputs, and then there's sort of tool layer, and then the output goes to this last layer, this last neuron, on which we then perform also this function, and we get the output. We get the float 0.1.
And the layer is basically just a vector.
And
With the weights.
sorry.
Sorry, that layer is just a vector. With the weights for the neural network, or how does it work?
Which layer?
What is a layer?
Okay, it's a little bit hard to explain. It is can for now just imagine that it's some function, some sort of very the neural networks are sort of very specific functions which are not actually that complex to write. So they always look like this, that you have some function that sort of looks like in this kind of way. It's either something like this, it's some non-linear function. It just takes it takes one number x, and it maps it to some to real numbers. So from minus plus infinity, or it can look in various different ways. So you have this kind of function, and then you have a sum of some weights times some inputs. So these are main components, and you put them together. So these layers are actually just a map of these kind of functions. So we have the whole the final function would look in following in all of the sort of simplest layer would look in the following way. You would have some kind of non-linear function, and then you would have this kind of sum. Well, this is basically just w1 x1 w2 x2 and so on. So if you have one neuron, then you take this axis, x1, x2, x3, and you get this output of one value, this let's say this is one epsilon. So this is sort of one, and then this is sort of this basic idea, and then you combine this idea into a little bit more complex. For example, this convolutional network is, as I described, you have more of these, and you sort of apply them. If you have any questions, just ask me.
I just wanted to step in and say that we haven't yet done a presentation on convolutional neural networks. So apologies for the sequencing, but that presentation isn't even in the making. Nobody has stepped up just yet. So we have to bear with Vašek now, pretend that we understand how convolutional networks work, and maybe one day we'll see how that happens. But it isn't, they're not that simple so that anyone can just stand there and explain it in 5 minutes. They are actually quite complex. So there will come a time, hopefully, we'll speak about them.
For now, we can just think that it sort of works like that, like I described. So that it may be more complex, and in Keras API, you can just use it in this way. It's sort of very simple. Provide few parameters. Here, I provide the activation function. I can describe that F function. So I'm saying that. So how this network actually performs? So based on the test data, which is made from this training data, which is separated part of this training data, it seems to perform quite well, but 92% precision. But in actual practice, from actual practice, I think I need some better way to evaluate it, because I wouldn't personally say it's 92% good. I think it's a little bit worse than that. So we can look at some examples. So, for example, here this is the original text, and this one was ran through the algorithm. So for example here, let's look at this dot. So this one, okay, so this one was predicted, okay. And we can look at these. This is some very common abbreviation. So okay, that was predicted. I think this JR is junior. So this was predicted.
Twice?
Yeah, it's twice. I don't know. That's some bug.
Can I have a question?
Some bug. Yeah, sure.
So, if I understood correctly, the network as an input takes 30 words.
Yes, so the one step is that 30 words, but it is then applied as a sliding sort of window. So you take 30 words, predict.
You begin with just one and add second one. In
Yes.
step one, you input only one word.
Yes, so that's something
And you
I
check
forgot to mention.
if the dot is after that word.
That's something I forgot to mention, is that it predicts, it has 30 words, and it predicts whether is there a dot in the middle, after the 16th word,
okay.
is there a dot or not? So that's how it works, and then you slide this 30 words across the text, and you go over each position, and either place or not place. Yeah, sorry for that, I forgot to.
So in step one, you have first 14 slots are empty. You have first word
Yeah.
15, and then next 15 words.
Yeah, exactly. And on those first 15 or 14 places, I put some padding words. I think it think the padding is however. So it puts however. So maybe let's evaluate quickly a bit more. So silence. This next one. Okay, so that was predicted. Book on. So here there is incorrect dot here. Book on manning. So that was not in the original text. So that's a mistake. Pressuring to beat him. So this is okay. Now then there is there's something hard to predict. So it just places dot here. So that's incorrect. Try it for 2 weeks. So this is okay. More insects. So here dot missing. Perhaps because of the and. And after and there is also dot missing because there is a comma. So that was trained to be also predicted. So but there's no comma here, not here. So you can see that you wouldn't say that it's 90% too good, but it's okay. You can use it in the use case. If I used it was okay. So let's look at this one. So well, okay, so that's a mistake. It was 6. Okay, that's correct. It was at this point dot. Okay, that's correct. But as I recall, okay, that's incorrect. For some reason, dot. That's correct. Okay, so that was all my presentation. Would you like to ask something? I can, if you want, I can go shortly into how specifically here the convolutional network sort of looks and try to explain it, but I don't have it prepared.
Question. So you said you train it on, and you have indexed 20,000 words, so 20,000 English words.
Mm-hmm.
Do you know like how big, how many English words are like in total? How big percentage it is?
Well, I think there must be a huge number, but when I was actually trying to determine for myself.
On the internet, a university graduate has vocabulary of 80,000 words in his head. So, 12-year-old child has 10,000.
So it's smarter, right? Better dictionary than
Could be like 15-year-old or something. 12-year-old. Something like this. I have some link in here in the code. I shouldn't have done that. Where I also was looking at if 20,000 is a good idea. I can stop it now. Okay, yeah.
How long is training?
Actually,
and it used like GPUs?
yeah, I used my GPU, which I thought I would be using for gaming, and I don't actually game at all. And finally, I'm using it. It's just some GTX 960. It's not best, but this trains around 5 or 10 minutes, so it's very fast to train, and it is mainly because of that graph network of the graph layer, that's actually not. So this layer, it's not actually a neural network. You don't train it. It's just something that you download and reuse, and it maps those words for you. And so they spent all the hundreds of hours training this thing or producing this thing, and then you just download it, reuse it, and just for your use case, you do a little bit of training, and it's fine. So that is common approach now. can do similar things with images. You can also download some pre-trained things, some pre-trained functions, and reuse them.
This word embedding is a very fascinating subject in and of itself. Did you consider using word2vec, for instance, or is that part of the glove embedding? Because I've never heard of glove, right? And have you heard of word2vec?
Yeah, I heard.
Is it an alternative to this, or this one uses word2vec, or what is the relationship between them?
So word2vec and this glove mapping are related because they both map words into vectors.
Yes.
And they, in some way, they produce similar outputs, but they are quite different in the way they are produced.
Mm-hmm.
If I remember correctly, this word2vec is actually produced using training some neural network, but so you have this kind of network and you run some text through it and you make sure that these vectors coming out are optimizing some function again. But this glove is not produced using training. It's produced using a different algorithm which has some similarities but is different. We can see that here it's described a little bit that it looks for word-to-word co-occurrent statistics. So it's sort of a statistical method as opposed to training.
Thank you.
So, what do you think? What are the limits of? What is the limiting factor of the success rate here? Is it like the training? How large the training set is, or the architecture?
I think the main limiting factor is probably the number of neurons in this middle layer, in this middle section. So this output, basically you cannot change this part and you cannot change this part too much because adding more words probably won't have much impact. But this in this middle part can improve a lot. So for example, maybe I could have used much more testing data and much more these convolutional these small convolutional networks. So I could have made this parameter much larger and have lots more of these. And if I configured it correctly, I probably could have gotten better results. But in fact, this configuration as it is it's already sort of optimized. So in this kind of region, this actually performs well. I was trying having four layers like this, trying to have different these values, and this is sort of the simplest and still well performing. So yeah, if I had more of these layers and better configured, it could perform better. Because the network would sort of have more weights and would be able to learn more things. Like this, it's limited. So any other question?
There are these components called like this code family. Is it from the TensorFlow framework or who gives that?
So this one comes from Keras, but in TensorFlow we have something very similar, and API is not that different. I'm not familiar too much with it, but it's not actually that different. It's a little bit more complex.
What is the logic in with this framework? So I know that the Python is fairly widely used with this, but I assume the framework itself is written in some C++ or some more advanced language. And how does this two correlate? So how much of the logic is in one?
So this Keras API is really just an API, and you can choose different underlying frameworks. So I think this Keras is purely Python, and then this TensorFlow under the hood. It's probably some C. I don't really know.
One more question. Did you notice like some patterns or some cases where this usually fails? Like some kinds of sentences where this is bad, like where the 8% of non-precision comes from.
No, I don't actually know I haven't noticed something in specific. I think it will have problems with this and. So putting dots, for example, before and, that will be probably very complicated. Then if you probably have sentence with very unusual words which don't fit into these 20,000, then probably also it wouldn't perform well. And
but it probably works better with YouTube captions, right? Because they already have some dots and commas included, like not all of them have some. So.
Well, if you have only those auto-generated ones, they don't contain any. But sometimes some videos do have completely filled in the captions, and in that case, the application doesn't attempt to add delete that and add its own. But some of them come with.
How do you handle unknown words?
Unknown words are replaced with unknown token. I think it's the last number before the limit. I think it's 20,000 minus 1. Maybe it's 20,000. I'm not sure. So if there is separate token just for that, so the network sort of is attempting to train also in these cases.
Are you aware of maybe Google attempting something similar? Because that would be the next step, of course, in the evolution of auto captioning their YouTube videos, right? So, are you aware of something like that happening within Google? Any preliminary results or something?
No, I haven't searched too much on that. I don't know.
It's hard to imagine that they would be content with the current state of art, right? As it is. So
I think maybe for their use case, it doesn't matter so much for them, because they want everybody to watch the video, and if they watch the video and the text beneath maybe doesn't have punctuation, maybe, and it doesn't matter to them too much.
Yeah,
It's displayed with the it's displayed in timed manner, so I think
it's just a bit of text at a time, so maybe that isn't so pressing.
But maybe they would add it. It would make sense maybe in future. There is actually a competition in this punctuating of this unpunctuated text, and this other project, this operational project, participated. I'm not sure now, but maybe they even won something. I didn't attempt to extend this to fully, commas, exclamation marks, and try to participate. won't do well when I would include those others.
Yeah, that's what I wanted to ask next. Like, is it really like more complex with more punctuation symbols than just with delta?
Well, you would have more outputs definitely. But maybe the cases
Like, what's
would
the
be more specific,
difference
yeah.
if you trained it 4 times for like for each different thing, and then just run it 4 times and check the probabilities? Would that work?
But there would have to be more outputs such that you could compare them. So you would say, so the network needs to say, do I rather think that it's exclamation mark, or do I rather think that it's question mark?
Well, the network gives you probability if there should be question mark.
Yeah.
So if the other one runs and it gives you the probability if there should be comma, and you pick the biggest, the
Yeah,
one that's
yeah.
most probable. Like, but,
Yeah,
I don't know.
that would have to be. They wouldn't be. It would still be one model, but there would be separate outputs. And as you say, maybe it would have also good chance. Maybe the performance wouldn't be that bad. I was actually aiming to create some application which I could sell on Google Play, but as it turns out, so firstly, you cannot call your application, cannot call your application YouTube Reader because it uses this trademark name and could be deceptive. And then also you cannot use the YouTube API in this, in unspecified manner. Basically, or in manner that you don't display ads. So I couldn't publish it. They just banned me.
How's your experience reading the transcript? Is it like sometimes you have to like stop and think about the meaning of the sentence, or is it fluent reading?
Yeah, it's the transcript contains errors itself, and then the punctuation contains errors. So sometimes this is confusing what is actually being said. Furthermore, I'm using it with text-to-speech often, so there's another error on top of that. So sometimes it's very hard, but you sort of get what's happening.
It's like Chinese whispers, right? It ends up being something completely different than what was actually said in the video.
You have to use the context.
Or your imagination.
For example, this part, tunnels to alleviate congestion. So, and there's no punctuation. So I mean right now.
It's quite interesting that it would punctuate the word destroying as its own sort of sentence. I guess.
Yeah, this is definitely a problem.
I guess when the network is deciding whether it will place a period somewhere, it isn't aware of the fact that it has already put a period right before that word, right? Because at a particular time you're always deciding about one concrete place, right? So maybe a natural extension would be to try to attempt to sort of delineate the whole sentences by trying to find the boundaries of a sentence rather than deciding at each individual place where to put a period. That problem would probably disappear because it would realize that a sentence with just one word is probably not something that figures frequently in the training set, right? So, but it's a completely different approach, right? It's a very different approach.
How do you handle capital letters? Like if you go for the embedding of the
lowercase.
Everything you lowercase everything.
Yeah.
Okay.
Even the
Because
names.
because the embeddings could probably have even values for, you know, the meaning of the word will differ if it's capital T and lower, starting with lowercase, you know. So
Maybe, but
definitely,
I think
definitely. Like if you download the GOP embeddings, it should distinguish between capital Trump and. So maybe you could improve even with that.
Yeah, that
If you
sounds
distinguish, I don't know how the YouTube
capitalizes
if
something,
it
so-
capitalizes some stuff, it could improve the result.
Well, maybe that's the problem why I put a dot here, because it capitalized the string, and usually, like after the end of sentence, comma comes the
Yeah, but
next
you
bit
just said
capital letter.
that he lowercase everything, so
The network doesn't sees only lowercase words. Doesn't
Okay. Oh yeah.
So yeah, that's why, for example, you lose this LA. There's LA somewhere. So that's-
Oh, under LA it's like free.
under LA, so it's lowercase. That's sort of. thing
So
that
you
could be
automatically
improved.
uppercase the beginning of the sentence. Then.
Yeah, uppercase, but I lose all the capitalization. So YouTube would place capital L, capital A here actually. So in the transcription somehow they know. Any other questions? So I think we can end at that. Thank you for attending, and see you next time.
Thank you.